changing the orientation, the moment of inertia does not changes. Is this clear to you people? Just by keeping the axis same, the moment of inertia, you will always get it to be same. It doesn't depend over the in which orientation you are keeping that particular body. Okay, so that is why I1 will be same. And even if I say is that you choose any axis passing through the center of mass, like in this way, just the thing is that it should pass through center of mass. You will get the same result to be as 2 by 5 mr square only. And the same results hold true for the that is the hollow sphere. Is this clear to you people? Because there is no plane over here that you are choosing Ix and Iy. It is very symmetrical body, and there is no need to apply the perpendicular axis theorem. Is this clear to all of you?
Yes, sir.
Okay, and yes, one more thing I need to ask you that we were actually see as we are going ahead of the course, we'll be requiring your previous part of the chapters. So I was thinking about to arrange the class daily or not daily, sorry, I mean every week 1 hour of class on the Wednesday after 9:30. Okay, IST I mean 9:30 IST. Will this work for all of you?
So will it be 1 hour or 1.5?
It will be 1 hour. It will be 1 hour. So like this is whatever the time for if you are not in the India. So I'll say that whatever the time we are taking the class, it will start like it's ending right now. It will start after half an hour. It will start right now. We are ending this up class right here. But on Wednesday, our 1 hour class will start after 1 hour. So I think that nobody will be busy at that time, and we can have that class of 1 hour. Okay, so what do you people say that should we fix this time for that particular one class of every week? That will be a backup class regarding your previous chapters. Yes.
So
Okay, so Athia is saying okay. Yes, Rasha, what about you?
It's okay, sir.
It's okay. Aman and Zunaira
sir, which day?
on Wednesday. I mean tomorrow.
Wednesday. Every Wednesday or only tomorrow?
Yes, every Wednesday on every
Yes.
week. Okay.
Okay,
So
sir.
what do you say?
Okay, sir, no problem.
Okay, Zunaira is also saying no problem. Aman, what about you?
That's fine.
That's fine. So I think we should fix this time. And even if not able to take the class tomorrow, so we'll take it from the next week. But this will keep this time to be fixed. Okay. From 9:30 IST or whatever I had told you that also according to you people, you can understand that time. Okay.
Okay,
So
sir.
we'll end up this class here only. If you have any kind of doubts in the today's session, so just most welcome. You people can ask it, or else we'll end up here.
Thank you, sir.
Okay, welcome.
Thank you, sir.
Okay, welcome.
Good evening, Aisha, Jaslin, Marwa.
Good evening, sir.
Yeah. So let's start with the. I think just we were about to finish carboxylic acid. Some reactions were pending. Little bit reactions were pending, and so hopefully we will try to finish it this chapter today. Just a second. We have discussed the acidic and basic strength, acidic strength of the carboxylic acids, and we discussed that the electron withdrawing group makes carboxylic acid more acidic. And this can be used to detect carboxylic acid. We have seen esterification, conversion of carboxylic acid to acid chloride by using PCl5, PCl3 or SOCl2. SOCl2 is the best reagent that is used for alcohols also. And amides, you have to heat them with the ammonia. If you heat with the ammonia, the carboxylic acid are going to change to amides by the removal of water from carboxylic acid and NH3. So we discussed decarboxylation reaction. Decarboxylation is removal of CO2. How it takes place, Marwa, decarboxylation. What are the reagents which are taken for the decarboxylation? Reagents for decarboxylation are NaOH and CO2. Heat. Okay. NaOH and CO heat. Soda and lime. Soda is NaOH and CO is lime. When you heat them, the CO2 is removed and you end up with alkane after the removal of CO2. Clear? That is decarboxylation reaction. Very important reaction to reduce the number of carbon atoms. Today, let's try to complete this chapter and we can start DNF block. Okay. Next is some more reactions. Just we are about to finish. Zelinsky reaction. Basically, this reaction is about it is the halogenation at the alpha carbon of carboxylic acid. Zelinsky, this is a very important reaction. So, any idea, Jesslyn, Marwa, Aisha, how do you do it and what is alpha carbon?
The one that is directly attached to the functional group.
Yeah, directly attached to the function group. This is the alpha carbon. Yes. And what you need to put halogen on this? Red phosphorus along with the halogen. Okay, X2. Halogen can be Cl2 or Br2. whichever you want to put on the alpha position, followed by hydrolysis H2O. Got it? Is it clear or not? You have halogen attached at the alpha position. Okay. And this is called alpha halo acid. Clear or not? We have to see this halogen is very important as far as the chemical reaction are concerned, because once you have the halogen, you can put the group of your desire. Okay, CN, NH3. Okay, whatever you want, you can replace that halogen by SN2 reaction, and you can get it converted. Is it clear or not? So Helmholtz Zelensky is basically the halogenation at alpha position of the carboxylic acids. Clear? Alpha halo acid. So this I hope is clear to you. Very simple reaction, but very important, because various places we are going to use it. Okay, let's do one problem which contain the application of this. Red phosphorus in Br2. Okay, followed by hydrolysis. Okay, and that is going to give us what? That is going to give us A. The A is heated with QH aqueous excess we get B. So what are these A and B? Very simple reaction. A already we are doing, so that I hope you will be able to figure out what is A. Yeah, Jesslyn, Marwa, tell me what is A? What should be A? Aisha?
CH3, CH.
A is, what is the IUPAC name of A? This is, you are going to put the Br, that's it, on the alpha carbon. And it is going to be CH3, CH, Br, COOH. So the IUPAC name of the A is going to be 2-bromopropanoic acid. Clear or not? Very simple. Just put the halogen and this is the alpha carbon. Don't put it on the beta. That is very, very important for all of us. Don't put it on the beta, okay? Put it on the alpha carbon, right? And if you treat it with aqueous KOH excess, what will happen?
OH will be attached
Yeah, that
to
is
the
SN2 reaction. Yes, the one which we discussed in haloalkane and haloalkane chapter. The OH minus is going to come and substitute the Br. So what is going to be the answer? This is CH3, CHOH, COOH. Is it clear? If you heat it with ammonia, it is going to be NH2. If you heat it with KCN, it is going to be CN in place of halogen. So conversion wise, this is a very good, very important reaction. And you can put the group of your desire on the alpha position, but first you need to have that halogen at that alpha position, right? Next is if we take the aromatic carboxylic acids. This is which acid? What is the name of this acid? Aromatic carboxylic acid. The one that contains the benzene ring. And the COH is connected to the benzene. What is the name of this acid?
Benzoic acid.
It is, yeah, benzoic acid. Got it? Or benzene carboxylic acid. So if we try to attach some group, okay, on it, so it will be where that next group is going to come. Where the next, if we do the ES, okay, where the ES, where the next group is going to come on this. Let's say, suppose if I want to do nitration, how am I going to do it? Nitration. What we used to carry out the nitration? Any idea? Nitration,
HNO3,
HNO3 along with,
H2SO4.
yeah, because you need to remove water also. HNO3, H2SO4, heat. So that is going to put the NO2 group. But with respect to this carboxylic acid, where the NO2 group is going to come in? Got it? Tell me. Where the NO2 group is going to come in? Is it going to come at the ortho position, meta position, para position?
Meta.
Meta directing. This is a meta directing group. Got it? All the electron withdrawing groups are meta directing groups. How am I going to put the BR at the ortho position? Or the meta position? How we are going to do the halogenation? How we are going to put the BR at the meta position? Tell me. What is the reagent which was used for halogenation? Reagent used for halogenation. Nitration we can do by nitric acid and H2SO4. And halogenation, we can take halogen Br2, but don't take light, right? HCl. Take FeBr3. FeBr3 is a Lewis acid catalyst that will help to remove Br minus, and that Br plus is going to get attached to the meta position. Is it clear or not? I hope it is clear to all of you. Okay. So COH is electron withdrawing group, and electron withdrawing groups are meta directing and deactivating. The rate is slower. But how can you prepare this benzoic acid? That also we need to know. From benzene, how can you get to the benzoic acid? Yeah. Gasoline. How can you get benzoic acid from benzene? Marwa, Aisha, how can you get benzoic acid?
Pregnant reagent. We can.
Benzene is there and you want COH attached to the benzene.
Oh. Benzene.
Then what should we use? So think of attaching a carbon atom. And once you have the carbon atom, how can we do the alkylation? We can do it very easily by taking CH3Cl, AlCl3. Clear? That will give us what? Toluene. Is it clear or not? And that toluene you can oxidize it. with KMnO4 OH minus, that is going to oxidize the side chain completely to carboxylic acid. And because it is a basic medium, so you need to take H plus and H2O to convert that CO minus to COOH. Is it clear?
Yes.
So this is how we are going to get it. Okay. So get the or you can, or there is one more method to prepare benzoic acid. Starting from benzene, take Br2 and FeBr3, that is going to put the bromine, that is halogenation, just like the above case. But in the above case, there was a COH group. So because COH was there, so you need to put the Br at the meta position with respect to COH. But in this case, there is no group all present, so you can put the Br anywhere. Once you have the Br, you can treat it with magnesium. What are we going to get, and what should we take after reacting in magnesium and ether, so that ultimately we get benzoic acid? What should we use? Tell me quickly. Yeah, Aisha, Justine. What tell me, am I audible?
Yes, sir.
So tell me how we are going to do it. What extra thing we need to add? Aisha, what extra? COO we want. Okay, so molecule, do you know any molecule which has C double bond? CO2. That is carbon dioxide. Clear? You can take carbon dioxide followed by acidification. So you are going to end up with benzoic acid. I hope this is clear to all of you. Any doubts on this?
No, sir.
Okay. Let's do some conversion, then we can move to DNA block. This already we have seen just now. So I hope you will not take much time to do this. This also we have discussed in the previous class. So A is what? What is the name of A? Jaslyn and Marwa, tell me quickly. Aisha, what is the name of?
Nitrobenzoic acid.
Yeah, meta-nitrobenzoic acid. Got it. This is A. This already we have seen just now. With SOCl2, what is going to happen? This also we have seen. I just told you today, and we discussed in the reaction in the previous class. SOCl2, PCl5, okay, that convert the OH to COH or the alcohol to COCl. It is going to become acid chloride, right?
Mm.
This is meta-nitrobenzoic acid, and it is going to become acid chloride. Nothing is going to happen to NO2, okay? Then if you take the reducing agent, NaBH4, what will happen? It is a weak reducing agent.
Yeah, OH group will be attached.
Which one?
COCl.
Yeah,
COCl becomes CH2OH.
yeah, it is going to become CH2H, exactly. So this is going to be a selective reduction, okay? Let's move on to some other problem. And because this chapter has aldehyde, ketone and carboxylic acids, both, this molecule is having ester and a ketone. This is the ester. Ester is exactly like the carboxylic acid, but instead of OH, you have alkyl group on the OH plus in place of H plus, and this is a ketone. Okay. So first I will take H3O plus. H3O plus is what? Water in presence of dilute H2SO4. That is ample amount of water. With that, what will happen? Normally H3O plus is taken for everywhere. It is taken for hydrolysis. Okay. So ester is going to get hydrolyzed. Then I'm going to take NaOH and CaO heat. That's also we have discussed. Or we can write the products one by one. With H2 plus what we are going to get?
Acetic acid.
It is going to form an acid, right? this ester is going to break. It will undergo hydrolysis, H and OH. It is going to give the carboxylic acid. Okay, that ester part is going to, but the ketone part is going to remain as it is. CH3, C double bond O, CH2, COOH, and CH3, CH2OH. So the ketone part is going to remain as it is. The carboxylic acid is going to end up with as ester. That ester is going to end up as carboxylic acid after hydrolysis. Okay. The alcohol part is going to separate. Next, we take NaOH and CaO. What are we going to get with that? Today, just at the beginning of today's class, we have discussed that what happens with soda lime heat. It is decarboxylation of carboxylic acid. COH is going to get removed. So you are going to, this is minus CO2. If the CO2 is removed and you need to place H plus in H in place of CO2, you are going to get acetone. And the next reagent also you are aware, and that is a very important reaction. It is a test. Two is a yellow solid. So which reaction is this? This is acetone, and I'm talking about this reaction. It is a famous name reaction. It starts from the word H, alphabet H. Yeah. Which reaction is this? Starting from H, it's haloform reaction. Is it clear or not? And haloform NaOH and I2. What happens? One of the CH3 breaks apart as CH as haloform, which is could be chloroform, bromoform, iodoform, depending upon the halogen which is taken. This is I2, so iodoform. CHI3, which is a yellow solid. Clear? Any doubts in this?
Yes.
Okay, haloform, do remember it, very, very important. Okay. So we have seen hydrolysis of esters. Then we have seen decarboxylation of the carboxylic acids using soda lime heat. Then we have seen the haloform of which is given by methyl aldehyde and ketone, and that also will give you a carboxylic acid upon acidification. Directly in the haloform basic medium is there, so you are going to end up with CH3CONA. If you take H plus, this is going to become CH3COH. So it is haloform reaction gives you a carboxylic acid and then halo. Okay. Now let's move on to the other topic, which is D and F block elements. What is the status of syllabus in the school? When are you going to have the pre-boards?
So November 17th.
By 10th?
No, after 2 weeks.
After 2 weeks, okay. So D and F block elements. There is some lag is there. Just a second. So D and F block elements. Okay. So this chapter consists of 2 parts. One of the part is obviously, as the name indicates, D block elements, which is the larger, which forms the larger part of this chapter, and a smaller part is the F block elements. Okay, which are not as large as D block elements. Okay. So first of all, when the element is put into D block, when an element is considered to be a D block element, what's the criteria? Is sodium a D block element? Potassium? Yeah. Yeah, Isha, Marwa, tell me quickly. When an element is considered to be a D block element, what's the criteria?
Usually metal.
It is a metal, yes, and when you put the electrons, the last electron enters into the D subshell.
D block.
Okay, so then it is considered to be a D block element. So where the D block is present, if you look at the periodic table, the groups are clubbed together as blocks. This is S block, okay, and this is the D block, and you have P block elements, okay. And A block elements, got it. Which is placed at the bottom. Okay. So D block, so the element is placed in D block when its last electron in the electron configuration, it depends upon its atomic number, right? First of all, and the last electron enters into the D subshell. Is it clear? For example, if you have scandium is the 21st element whose atomic number is 21. So can you tell me the electronic configuration of scandium? What will it be? There is a shortcut way to write the, either you can start from the scratch, 1s, then 2s can hold 2 electrons, then 2p can hold 6 electrons. The p subshell has 3 orbitals, okay, so 6 electrons. Each orbital can hold 2 electrons with opposite spin. You have already studied in your class 11th, okay. Then you have 3s, then you have 3p, okay. Till now you have filled how many electrons? Very important to tell. How many electrons are being filled till now? Marwa?
18.
18. Yes. Why I'm asking this 18? Because this represent the electronic configuration of a noble gas argon. Okay. Because every time we are not going to write it like this. Okay. Because otherwise it is going to be a very cumbersome task. So what we do is the inner electronic configurations are not written in detail. They are represented by the noble gas preceding noble gas, by putting the symbol of preceding noble gas. Only the outermost electronic configurations are mentioned. Then you have 4s. As per the energy, the 4s is having lower energy. So the trick is 4s, it is outer, but it is having lower energy. Okay, then 3d. So for the first transition series, the trick is very simple. If it is 21, just put 2 and 1. Got it? So scandium electronic configuration is argon. Atomic number is 21, means 4s2, 3d1. Got it? If it is 22 titanium, what is going to be the electronic configuration of titanium? Argon 2 and 2. Okay, 4s 2 and 3d2. Okay, because 4s is filled first, though it is the outer shell, because n plus l value is lower. Okay, then d. Because the last electrons are entering in the d subshell, that's why these elements are d block elements. Okay. Similarly, titanium vanadium is 23rd element. Very simple to write the electronic configuration. Argon 2 and 3, 4s2, 3d3. Okay. Just you have an exception with the chromium. That is very important. Chromium, first I'm going to follow the normal routine procedure which we are following, and that is argon 4s2, 3d4. This is the routine which we were following. But this is not the electronic configuration. There is a slight change. So one of the electron of the 4s gets transferred to 3d. Is it clear? What's the reason for it? So this is the correct electronic configuration. So why this slight minute change has happened? It's because of the d subshells have 5 orbitals. Okay. when these d orbitals are singly occupied, they are half-filled and they are very stable. Okay, because of this symmetrical electronic configuration. So why this exceptional electronic configuration is there? It is because of the due to you are going to say due to the extra stability of half-filled. So what you did, just D subshell was just one short of becoming half-filled so what you did, you took one electron from 4s and transferred it to 3D. So that the 3D can attain half-filled electronic configuration containing one electron in each of the d orbital, and that is going to make it very stable. So this happens due to the extra stability of half-filled d orbitals. Okay, this is one thing you need to remember. The other thing is which you need to remember is what is the other name for d block element? They are all metals. Okay. S block are metals. P block on the extreme right hand side you have non-metals. Mostly non-metals. But along with them, you have some metalloids. And you have some metals also, like aluminum, which is a metal, lead, which is a metal. It is a part of the P block. Clear? So what's the other name for the D block elements?
Transition element.
Yeah, transition metals. And why they are called transition? And what's the exact definition of transition metal?
Partially filled orbit d orbital.
Yeah, partially filled D subshell, either in their atom or in their ion. They are called transition metals because they have incompletely filled D subshell. But not all of the D block element are transition metal. Okay. As you move from left to right to, so which is the next element?
Iron.
Iron, cobalt, nickel, copper and zinc. Okay. And the exceptional electronic configuration is for manganese. Is the 25th element. So we can quickly we can apply that shortcut method to write the electronic configuration of the manganese. What it is going to be? 25th element. Okay. So as I told you, 2 and 5. 4s2, 3d5. Iron is the 26th element. 4s2, 3d6. 26, 2 and 6. Okay. 27, 2 and 7. 28th, 2 and 8. That innermost electronic configuration will be same as that of argon. That you are not going to write again and again. In the copper, you have exception again. And the same reason is being followed in the copper also. So copper, the electronic configuration is argon 3d10 4s1 due to extra stability of completely filled d subshell, that one electron has been transferred to 3d. Got it? And zinc has completely filled d subshell. It is the 30th element. Zinc, below zinc you have cadmium and mercury. So zinc, cadmium, mercury are not considered as what? In the electronic configuration, if you look, they have completely filled what? D subshell. Okay, the copper also has completely filled D subshell. But in the ions like copper plus 2, okay, copper plus 1 is what? What is the electronic configuration of copper plus 1 and plus 2? Tell me quickly. Copper plus 1 and plus 2. Plus 1 means you have to remove that one electron. And electrons are always removed from outermost shell. So cuprous ion is going to have electronic configuration of argon 3d10, and one electron from the 4s has been wiped out. Copper plus 2 is argon 3d9. So copper can have incompletely filled D subshell, but not in its atomic state, but in its ionic state, which is carrying plus 2 charge. So copper is a transition metal, but zinc is not a transition metal. Similarly, the cadmium is not a transition metal. They are D block elements, but not transition. Is this clear?
Yes.
Because they have completely filled D subshell in their atomic state and also in their ions. Their ions they form as plus 2. So plus 2 ion, there you remove 4s electrons. So in the ions also you have the D subshell completely full. So they are, because of this completely filled D subshell, they are not considered transition metals. Clear? Very important, because this is the first question which we encounter in this, in while discussing D block. This is the first level of question which we see. That what's the difference between the transition metals and D block metals. Next is, if we get into similarly the F block element, like the D block elements are known as transition metal. What's the name for F block element? Can you tell me quickly?
Inner transition.
Name for F block element?
Inner transition.
Inner transition. Yes. Okay, and in each D block, you have 4 transition series. Okay. What are these transition series? 4 series are there in the D block elements. So these are the D block elements. So you have 4 rows of element. Is it clear or not? This is the first row of element is 3D or known as first transition series. The one which we have written just now, that starts from scandium and ends at zinc. Why it is called the first transition series or the 3D series? That is quite clear. It's because the electron enters into the 3D subshell. You can see in every subsequent element the 3D subshell is being filled with extra electron, which is coming with the increase in atomic numbers. Okay, clear or not? Similarly, you have 4D transition series, which is the second transition series. I'm going to write it in short form TS. 5D transition series, which is the third transition series. And 6D transition series, which is the fourth transition series. Is it clear or not? And this is starting from scandium and ending up to zinc. Like it can start from yttrium and ends at cadmium. It starts at lanthanum and ends at mercury. Clear or not? So there are various transition series present. Okay, and elements of the first transition series. If we look at the electronic configuration, excuse me, only the chromium and the copper shows abnormal electronic configuration. Is it clear? But if you move to second and third transition series and the fourth transition series, you will see a lot of variation in the electronic configurations because of the larger orbitals involved and their closer energy gap. Okay, you will see a lot of variation in the electronic configurations. So this transition series, which is the third transition series, which starts from lanthanum, is not continuous. Okay, there are 14 elements which are which lie after lanthanum, but because of their electronic configuration, their outermost electron, the last electron, is entering into the F 4F subshell. So this is the 4F series, all lanthanoids. Similarly, there are 14 elements which are filled after actinium, where the electron don't enter. The last electron is entering in 5F, and if it is not entering in D60, if it is entering in 5F, they will placed in the F subshell, F block elements, okay, along with the F block element, because these elements of 4F are followed by lanthanum. They are called lanthanoids, and the elements which are F block elements, which lie after actinium, are known as actinoids. So this is the F block. F block consists of 2 rows. Okay, like the D block consists of 4 series or 4 rows. First transition series, second, third, fourth, okay, 3D. We can't have 2D because D subshell is not present in the second shell. Okay, so at least we should have 3D, 4D, 5D, 6D. Okay. But in this 5D transition series, the 4F is being filled first. And in 6D transition series, 5F is being filled first. So those elements where the electron is entering into the 4F or the 5F subshell, they are not placed along with the D block element, they are placed downward. Okay, and this whole block is known as F block element. It constitutes 2 series, 4F series and 5F series. 4F series are considered to be lanthanoids and 5F series are considered to be actinoids. Is this clear? Any doubts in this? Aisha, Marwa, tell me. Jaslyn,
No, sir.
very easy topic, but very important because a lot of discussion is there in this. And your explanation should be clear and precise, okay? Whatever they are asking, just answer that. Clear? No need to write extra points and lot of theory, no. Whatever being asked, just write that, and that's how we are discussing. We are discussing it in a very precise manner, what each term means and what's the significance, okay, and how these terms are responsible for uh, naming those particular metals, okay, lot of things. Okay, now we are going to discuss the properties of the D block elements. So properties of the D block element, first is the periodic variation of properties, because they are, each element is not separate, they are actually the neighbors one after another. So you see gradual variation of properties as you move from left to right across the period, or as you move down. Clear? So the first property which we are going to discuss is the variation of their size or atomic radius. Size or atomic radius, how it is going to change. First, you are going to discuss the variation as you move from left to right across the period. This is the variation in each transition state. So how the size of the atomic radius vary when you move from scandium to zinc? What are you going to say? Yeah,
It
Aisha, Marwa,
increases.
Jaslin. Yeah. Yeah, Aisha, tell me. How the size vary as you move from left to right across the period? Will the size increase? Will the size decrease? Or a mix of both?
Both.
Yes. Initially it goes down. In iron, cobalt, nickel, it remains constant, nearly same. And it increases towards the end. Why the size is not increasing? First tell me. Why it's not absolutely increasing? What's the reason? Left to right. You have the electronic configuration, the one which we have written just now. So why the sizes are not increasing? Yeah, Isha, Marwa, Jaslin, tell me why the size is not increasing. Why it's decreasing and then more or less it is same, okay? That we can say. If you compare the size of the first element and the last element, they are always they are nearly same, okay? So what's the reason? The reason is electrons are added to the same shell. They are entering in the same 3D subshell. It's not like they're entering in 3D, 4D, 5D, not like that. Or not like they are entering in the fourth shell, then fifth shell, then sixth shell, not like that. They are entering in the same shell, in the same 3D, and the protons are increasing, so protons are causing more attractive force on the electrons. That's why the size is expected to decrease. Is this clear?
Yes.
Electrons are added into the same shell. Protons are increasing, that's why the size decreases. But then why it is start increasing towards the end? Copper and zinc, you see that all of a sudden the size has started increasing. What's the reason? Because of the repulsion of the electron, they have completely filled d subshell. So towards the end, we have how many d electrons? Jaslyn, how many d electrons are there in the copper and zinc? 10. They are fully paired, completely filled d subshell. So those d subshell may cause repulsion. Okay, because they have that d10. But before this, copper is d10 because of the exceptional electronic configuration just now we discussed. The zinc must be d10. Okay, so both of these elements, the size is expanded little bit. Okay, and that's why they gone up. Is it clear or not? Got it? Next is down the group. What happens down the group? Size should increase or decrease? Suppose if you are having scandium, yttrium, lanthanum, actinium. Titanium, zirconium, hafnium. They are one below another. So what do you think of the size as you move down?
Mm,
Should it be more or should it be less?
more,
Yes, more. Why?
because there is extra energy level.
Yeah, because a new shell is being added in every subsequent element. In the first is 3D, 4D, 5D, and 6D. Is it clear? But there is a surprise that the size of the 4D and 5D series are nearly same. It is because in the 5D series you have F block elements, and F block elements cause contraction in size. Okay, so down the group size increases. That is one thing. But the second and third transition series element have nearly same size. For that, you are going to write the reason as contraction due to F block elements, because here we have F block elements, right, which are not placed here, which are placed below this. So once we have the F block element, then we again resume our metals of the D block. But those F block elements have the smaller sizes, and the D block which are following those F block element, they too have the smaller size. Is it clear? So size should increase as you go down, but the second and third transition series nearly have same, or the fourth transition series also have the nearly same size. The size doesn't increase much because of the F block elements, and they are smaller in size, and the D block elements which continue after those F block elements are still smaller. Got it? Clear or not? This is very, very important. So titanium is there. Zirconium is bigger than titanium because it is below. But hafnium and zirconium are nearly same. Got it? Clear or not? Very important to know. Likewise, you have vanadium, niobium, tantalum. Okay, so niobium is from the second transition series. It is expected to be bigger than vanadium. Okay, more electrons are there in it. Vanadium is 3D and that is 4D. And tantalum is nearly same as that of niobium. So what reason we are going to get? Marwa, tell me, Christine. What reason should we get? This is going to be the you can say due to the presence of F block elements or lanthanoid contraction. You can use the word. We are going to see what is lanthanoid contraction. In F block elements. So F block, all of a sudden, where the F block elements have came into picture, we are discussing D block. How F block? F block as elements are there in the third and the fourth transition series. Okay, they are there a bit in the middle. Okay, some F block elements are there, but they are not, though they are there, but they are placed at the bottom. And that actually because they are but they are there, so the elements following them will have smaller sizes. Why block elements have smaller sizes, that also we are going to discuss, okay, very quickly. So this is clear. Size. The next property of the D block elements which we are going to discuss is this is the atomic radius. Okay, atomic radius is the size of the various elements which we see. Okay, next is the ionization energy. Or ionization enthalpies. So what do you mean by ionization enthalpy? First of all, we should discuss that. And if you take scandium, so it is the energy required to remove the outermost electron of the valence shell from an atom in the gaseous state. So how much energy is going to be required to remove this electron? Delta ionization. Okay, you could write it like this. H, and it is positive. We are going to give some energy to remove the electrons. Clear? This is first ionization energy. If you want to remove the second electron, one being already removed, so you have scandium plus. You are going to end up with +2 charge ion cation because you have also removed the second electron. And this is going to be delta. This also energy need to be given. So this is the first ionization energy, or you can simply write it IE1. That's a more easy way to write IE2. And as you are removing more and more electrons, IE3, IE4, okay, so energy required to remove the fourth electron, third electron, IE3. Energy need to be provided. And this energy, how that energy varies for a single element and for the subsequent elements, okay, that is going to play a very important role in the formation of the cations. From that we can make out that which cations are going to form and easily, or which cations are very difficult to form. And because if the ionization energy is going to be too high, the cations will be very difficult to form. Okay, so that discussion we are going to continue in the next class, right? So let me end today's class. Just go through your carboxylic acid chapter, NCERT, and let me know if there is any doubt. Okay, just solve the back exercise. Is it clear or not? So that will help you a lot. Very important. Okay. So let me end the class. Bye bye. Good night. Take care.
Thank you, sir.
Okay. Bye.